Okay, we're going to look at absolute max, absolute min, local max, local min on closed intervals. And we'll kind of treat these as though they're AP problems. We'll do the first one with no calculator. We'll do the second one with a calculator. And my mistake, but these should be brackets, not parentheses, because we do want to include -6 and 3 and do want to include 0 and 6. So my bad. But the idea is, and we'll refer back to these, that in order to find absolute maximum and minimum values on a closed interval, so that means that we don't, our interval is not all real numbers, okay? We have very specific values that we're looking at the function over. And the first thing we want to do is we want to check endpoints. The second thing we do is we find critical values. And then finally, three, we plug the critical values back into the function to get our actual y values. And so let's just check this right now. What graph does this make? It makes a parabola, okay? And if we wanted to, we could actually graph that and find out exactly the shape and what it looks like. In fact, do you remember what a parabola looks like? Do you remember how to find the vertex? Very good. Negative b divided by 2a. And we're actually going to prove that in about 2 minutes that that is the vertex. And so we do negative b divided by 2a. So negative b would be positive 4 divided by twice the a value is 2. And so 4 divided by 2 is 2. So 2 is the x value. I plug it back in to get the y value. 2 squared is 4, minus 8 is -4, plus 3 is -1. So we know that this is a parabola whose vertex is at 2, -1. And which direction does it go? Up. I can also tell something else interesting about it. It looks like it actually has a y-intercept of 3. And so I could find the x-intercepts as well. Looks like they're 1 and -3 for the factor. But I'm just going to quick sketch a graph here of this parabola, just like that. Okay? So it's good enough to sketch. I didn't have to find all the properties of it. We did that last year. Good enough to get a sketched graph. So the question is, what does this graph look like just over the interval 0, 6? In order to look at what the graph looks like over the interval 0, 6, I need to do that first step, which is check the endpoints, meaning find f of 0. What is f of 0? 3. And then find f of 6. 6 squared is 36, minus 24 is 12, plus 3 is 15. My endpoints, okay? So I'm checking my endpoints, as it said in the very first rule. Check the endpoints, plug in f of a and f of b. All right? So 0, 3 would be right here, correct? And then 6, 15 would be, something like that, right? So I don't want to look at the entire graph. I just want to look at the blue part of the graph. By looking at the blue part of the graph, obviously, what is the absolute maximum value? 15. Would you agree? What is the minimum value? -1. And so what we want to do is we want to show that we're able to check and be able to find the absolute min and absolute max over that closed interval. And the way we do it is we check the endpoints, but then we also check for our critical values. Critical values happen when the derivative is equal to 0. So take the derivative and you get equals 0. So 2x is equal to 4. So x is equal to 2. Are you surprised that a critical value happens at x equals 2? No. You plug the 2 back in and you get -1. We've already computed that, correct? So therefore, we can tell by looking at these values, f of 2 is -1. Which one of these is the largest value, 3, 15, or -1? So absolute max is 15. Which is the smallest value? So you can tell by our work that we're able to determine by checking endpoints and checking where the derivative was equal to 0 that we have an absolute max of 15 and an absolute minimum of -1. If we would have checked the endpoints, we would have missed the -1, right? If we would have not taken the derivative and set equal to 0, we would have missed this, what we call hidden behavior, right? I mean, 3 is not the smallest value. It goes all the way down to -1, okay? So that's quadratic. This is cubic, and it changes for each one. But one thing I want to show you guys, notice that the vertex, we ended up finding by taking -b divided by 2a, but it also worked out when we took the derivative and set it equal to 0. So one short thing I do with people during this time is, this is the kind of the equation for a quadratic, ax squared plus bx plus c, all right? And if we want to take the derivative of that and set it equal to 0, note that a and b and c are just constants. They're just numbers. So what would be the derivative of ax squared? 2ax. What's the derivative of bx? B, derivative c. So if you solve where that's equal to 0 and you solve for x, you get 2ax is equal to -b. And divide by 2a. So we've shown that the vertex is -b divided by 2a. I mean, calculus can do that for so many of the formulas that we've had all over our time. In fact, all these geometry formulas here, we can prove just about every single one of them using calculus later on. And so it's a good time. Yeah, it is. So let's try a little bit more challenging of a problem. You're going to make sure you have your calculator out for this. Okay, we'll call this a calculator problem on the AP exam. And we haven't really started studying yet. You can look here, problem 44 from 1998. It does say that you should use your calculator. All right. So you know we want to keep that in mind, that there's some problems we will use our calculator for. So I'm going to show you some neat things that you need to keep in mind with your calculator when you do these kind of problems. First of all, I'm going to take out my calculator and I'm going to sketch the graph. Because although I know what a cubic looks like, I don't know all the hidden behavior in there. So I'll go 2x to the third plus 3x squared, and then minus 36x plus 4. And I'll just view it in a standard window, and I get this kind of shape, right? Sure would like to see the top and bottom, right? That would be nice. And there's a really easy way to see the top and bottom. Would you agree that the max might happen somewhere around a value of, say, -3 or something like that? I mean, so if you calculate a value of -3, it tells you it goes all the way up to, say, 85 or so. So I'm going to change my window so that I can make sure I see everything. I'm going to change the X window is fine, but the Y window, I'm going to go -200 to +200, and I'm going to put a tick mark every 100 on there so I can see it all. Now as I graph it, oh, tick mark every 10. That's a better looking graph, isn't it? Okay, so first thing is, can you actually see the graph by adjusting your window? So let's draw that shape here. And you guys are used to using your table values, and that's fine. But in this situation, I really encourage you, don't use your table values. Use this other option that we have. Use your option for simply value. So you guys remember, if you go to your table, you can type in values like -6 and +3, and you can come up with the outputs, right? We can also do it using our value function. We'll try that when we get back. Go get some brain food. You got about 5 more minutes, and you have work time. Okay, so here we go. Turn on. Please don't reset. Calculator reset. There we go. All right, good times. Okay, so I'm going to go into y equals, I'm going to type in 2x to the third plus 3x squared minus 36x plus 4. And as I look at that graph, we said before, I can't see the whole graph, so I will go into my window. I'm going to change my y values to -200 and +200 because we came up with an indication the values would be somewhere around there. And now as I look at my graph, it looks pretty. So there we have it. It's the graph that I sketched there. But the question is, what are the absolute min and max values? In order to determine this, I need to check the endpoints. I need to check where the derivative is equal to 0. So let's check the endpoints. F of -6 is and I don't have to go into the table to do it. You can do second calculate and choose value. When you punch in -6, it gives you -104. And then when you calculate value again, you get -23. So you can see from this drawing that we only want really the green portion of the graph. We just want that segmented portion. And so we get -104 and -23. But that doesn't tell us necessarily the absolute min and max. We also need to check our critical values. And that's where the derivative is equal to 0. What is the derivative? Factor out the 6. So therefore, along with checking f of -6 and f of 3, I need to check f of -3 and f of 2. And again, go ahead. Yep. If I punch in -3, I get 85. I don't have to check 0. Are you thinking because of the 6? If there was an x, then you would have to check 0. Um, value, and I try 2. And as I do, I get -40. So I'll now answer the question, what is the absolute max? 85. What's the absolute min? -104. Well, you can plot them if you want. That helps you. So if you want to plot them, that's fine, but you sure don't have to do that. Again, the question is, what's the absolute value and absolute min? So you could solve the problem any way you like. This is the way in which I went about it. You want an assignment. Good for you.